Hello everyone, I'm Shubham Rai. I'm a PhD student at Chair for Process Design, TU Dresden. I'm going to present our work on metastability with emerging reconfigurable transistors, exploiting ambipolarity for throughput. So first of all, let's go through the outline of the presentation. I will first introduce the ambipolarity phenomenon in reconfigurable FETs, then the design of metastability-based DRNGs using RFETs. In this, we will explore the digital circuit design and we'll see the simulation results. We'll also compare it with an equivalent CMOS-based circuit. Ultimately, we'll look at the statistical evaluation of the proposed RFET-based true random number generators, followed by summary and future directions. So first of all, what is reconfigurable FETs? So reconfigurable transistor technology is exhibited by a transistor made with various materials such as silicon, germanium, or even complex materials such as molybdenum ditelluride. They are also available in various geometries, both one-dimensional such as silicon nanowire, graphene nanoribbons, etc., or 2D dimensions such as molybdenum ditelluride planar sheets and even graphene sheets. RFETs are multi-gate devices. That means that on a single channel of the transistor, we can have multiple gates stacked on each other. And it follows a similar CMOS-like top-down fabrication process. So that warrants easier commercial feasibility to the silicon nanowire-based RFETs. In this presentation, our focus technology is gate-all-around silicon nanowires. The only reason was that it's one of the most developed RFET technology with proper Verilog A models and physical synthesis flows. On the right-hand side, you can see that we have this silicon nanowire pictorial representation done by or proposed by these two works. And you can see that we can have multiple gate terminals on a single channel of the transistor. So what do we mean by multiple gate on a single channel? So basic structure of an RFET says that on the technology itself, we have two types of gate terminals, the program gate and the control gate. So program gate selectively blocks undesired carrier types, and it gives the P type and N type functionality to the device. The control gate, on the other hand, controls the carrier flow and provides input to the logic function. The control gate is similar to what we have the gate terminal in a typical CMOS device. Now, looking at the right-hand side of the slide, we can see that a typical RFET can be modeled into using two CMOS, one of PMOS and the other of NMOS, connected to a MUX. Now, this gives a MUX type functionality, which is here in case of RFETs is intrinsically generated due to ambipolarity. This leads to compactness and inherent runtime reconfigurability for circuits and logic gates. You can see that the program gate basically controls, since it controls the type of the device, it goes as a select line in the MUX. Moving ahead, what is ambipolarity then? What does ambipolarity means in case of RFET? So ambipolarity basically means that in both the functionality, what kind of voltage to current transfer curves we can observe. And we can see that in case of an RFET, the P and N type functionality is almost symmetrical. And this is also important considering the future circuit implications. And also for exploiting this ambipolarity for logic circuits. Moving on, why we use RFETs for digital circuit design? So the first important thing is that it leads to reduced number of transistors for logic circuit implementation. This can be seen from the two figures on the right-hand side, where we have the XOR gate, which consists of just 4 transistors. And on this side, this is a minority gate, which basically can be switched to a 2-input NAND or a 2-input NOR based on the functionality of P. Now we can see that here we are using the intrinsic reconfigurability of the individual we are using the intrinsic reconfigurability of the individual transistors here, and hence the very small XOR gate has been realized. And this again corresponds to the fact that we are getting enhanced functionality from individual devices, which leads to more functionality per computational unit. Multiple independent gates since, as we said, that it's supported by RFID, so the other important aspect of that it exhibits lower logical and parasitic efforts with respect to CMOS due to less channel resistance per input. And hence faster logic circuits with even more inputs are possible, which is generally avoided in case of CMOS, where the cascading of transistors lead to slow performance of logic gates. In the present work, we now focus on how we exploit the metastability in case of RFIDs, and how we exploit the ambipolarity to get a double metastability condition in case of RFID-based structures. So on the left-hand side, you can see that there is a similarity to what an SR latch looks. However, the interesting aspect is that these two cells are basically the NAND NOR cell. Now, what happens that these NAND NOR cells are reconfigurable. That means that it can be configured as NAND or NOR. This configuration is taken care by the clock program signal. Now, if I look at the table below, we can see that if the clock program equals to 1, the functionality is NAND, and if the clock program is 0, the functionality is NOR. And we can see that if A and C are given as a value of 1, and the input switches from 1 to 0 or 0 to 1, we are getting a metastability conditions. Now, this is not possible in case of CMOS because you have fixed functionality. But however, because of the ambipolarity, since the logic functionality switches from NAND to NOR, we are getting two metastable states within a single clock cycle. This we can see here. So suppose we have this clock program signal and we switch the clock program signal like this. So with the input variation, we can have two outputs, both zeros and one. And these two outputs are a result of the metastability which has been observed in this SR latch based on RFID. It is to be noted that there has to be a bit of skew between the clock program and clock input. And in our experiment, we have taken it at 3 nanoseconds. Moving ahead. So ultimately, we can see that the random bits generated at both edges of the clock leads to twice the throughput. And this is what the most important claim of our work is. Now we see that we have two output bits being generated at each clock cycle. Now, the point is that how we can tap these two outputs. And for that, we need a flip-flop, which can also basically can take both the output bits. For that, what we did was that we take the RFID-based TSPC-D flip-flop and we make it as dual edge triggered. Now, in this case, what happens is that for the value of P, which is at the VDD and the VSS, we get a negative edge triggered flip-flop and also a positive edge triggered flip-flop for value of P equals to 0 and 1 respectively. So at the left, we can see that this is a TSPC-D flip-flop, which can be reconfigured at runtime to give both positive and negative edge triggered flip-flops. Now, the application of such dual edge triggered flip-flops can be huge, but in this case, we're using it for tapping the metastability states. On the right-hand side, the CMOS-based TSPC-D flip-flop is a positive edge triggered flip-flop, and you can just simply note that the number of transistors required in case of RFID is just 8, whereas in case of in CMOS, it's 11. And also, in case of RFIDs, we have both the triggering possible. Now we can say that this has implications that, as in case of RFID, that less transistor with more functionality or with multifunctionality. This because of the lower cascading of transistors, and because the RFIDs are basically Schottky based devices, it also leads to lower leakage. And also, as we told earlier, that the RFIDs have less parasitics and have faster performance. This can be very well. This has been experimentally verified in Cadence Virtuoso with the Verilog A model of RFID with this design. What else we have done is that we have XORed the outputs from multiple TRNGs as it improves the entropy of the resultant bit stream. XORing outputs in case of TRNG is a standard procedure, as it leads to, as we said, increase the entropy of the resultant bit stream. And the random bits generated by the true random number generator sample at the output node. The CMOS equivalent, however, will be like this, and the same functionality in case of RFID as in case of the RFID implementation, but with additional digital logic blocks. In comparison to CMOS, we can see that the RFID based design leaves good saving, and it is a superior design because it leads to a dynamic power saving of 70%, leakage power saving of 94%, reduction in power delay of 77.3%, and reduction in the number of transistors by 60%. We assume that these results are applicable when we have proper left and liberty files in case of RFIDs, and this can be actually realized for RFID based designs. Additionally, apart from these savings, we are also getting a throughput increment of the double of the frequency of the clock, and we are getting a throughput of 200 megabits per second, whereas the clock frequency is 100 megahertz. So once we have proposed this TRNG, the next step was to evaluate it statistically by using some standard benchmark suits available, such as the NIST benchmark suit. So what we did that we generated 110,000 bits for the proposed TRNG, and we use it at frequency 10, 100, and 200 megahertz. Then we take 10 binary sequence with 1,000 bits in each are formed from the 110,000 sample bits for the 3 operating frequencies. Then the 10 sequences for each frequency are subject to NIST SP822A test to assess the randomness. So the NIST, what are the NIST SP822A benchmark suit? It consists of tests which detects the non-randomness in a binary sequence, and each test results in a p-value, that is the probability that a perfect RNG would have produced a sequence less random than the sequence that was tested. The p-value should be greater than 0.01 to be termed as success. And we perform multiple iterations for each of these tests so that we get a more generalized result. The proportion for success for each test is then measured, and another metric called p-dash value quantifies the uniformity in the distribution of all the p-values for each test. This is important because the random number has to follow a uniform distribution. Ultimately, if the p-dash value is greater than 0.0001 and S rate is greater than equal to 0.954, we can say that a test has successfully passed. Now, without the post-processing, which I will come in the next few slides, the result of the NIST 822A test with the bit stream produced from our TRNG, we can see that this is the result. And obviously, some test cases are passing at some of the frequencies. However, some are also failing at some of the frequencies that are uploaded the higher frequency. But one important consideration or one important point which we should have to look here is that the monobit frequency test is passing for both higher and lower frequency operation. Now, this is one of the most critical tests. It's the necessary test in the NIST benchmark suit to pass for any randomness check. It implies that proportion of zeros and one produced by the TRNG can be deemed uniform as expected by a truly random sequence. Now, let's see what happens with the post-processing of the raw bit stream. What we did was metastability latches are weak sources of entropy, and when actually implemented on hardware, biases do exist. However, in case of RFID, this is not due to process variation, but obviously there will be some process variation, but the ambipolarity is bringing the double throughput into picture. Thus, these TRNGs are typically interfaced with post-processing unit that transforms the raw bit stream into sequence, which is computationally tedious to differentiate from a purely random sequence. Post-processing is also used to compensate for PVT variation and inference effect. Since in the previous statistical evolution, only a few benchmarks failed, we use a simple post-processing technique called von Neumann extraction on the output raw bit stream from the TRNG. So what is the von Neumann extraction? It says that if the bit pair is 00 or 11, then we will reject the bit pair. However, if it is 01 or 10, then we will take 0 and 1 respectively. So the raw bit stream is grouped into non-overlapping pairs of consecutive bits. For each pair, in case both the bits are equal, then we discard the pair, and the algorithm uses two output bits, input bit, to produce either 0 or 1 output bit. So obviously the frequency goes down, and we carried on the same experiment as we did, but with von Neumann extraction. And we can see that with post-processing, the results are much better, and almost all the test passes as compared to without post-processing. Note that this post-processing algorithm is not a qualified or a standard cryptographic function or a randomness extractor. It is solely used to show that the generated bit sequence has sufficient randomness to make it pass with the NIST test suite. So we can see that in this work, we propose the design of metastability-based true random number generator using emerging reconfigurable nanotechnology. The major focus of this work has been to explore how Ambipolarity can be exploited or enhanced throughput for random number. Using runtime recon, the RNG is shown to use less hardware, be compact in terms of transistor, and also consume less power and have a low critical path delay as compared to CMOS equivalent. And future work direction includes stochastic modeling of the RFID-based latches as proposed for the CMOS-based metastable circuit, plus followed by Monte Carlo simulations to show PVT robustness. Thanks for your attention, and I welcome you all with your questions.